Yeah, good afternoon, everybody. 1 second. Yeah. So, in the last class, we were discussing about the connection between the shape of the brain and intelligence. Actually, it's a slightly vague question. We began deliberately with a slightly vague question. That is there any correlation between brain shape and intelligence? So, we began looking at Einstein's brain, the anatomical data from Einstein's brain analysis. We found that there's nothing very exciting, nothing very sensational about Einstein's brain compared to normal brain, which is expected, but it's nice to start with a simple and a kind of interesting question. So then we began to look at some of these brain to body ratios, right? And then we came up with this quantity called encephalization quotient, which is more interesting than simply looking at brain size and brain shape, but still not very convincing because it just looked like some kind of a curve fit, right? You just want some index which is highest for humans, and so we are able to get it. So that's not very convincing. So then we began looking at some of the connectivity patterns in the brain. So basically some kind of factual data about neuroanatomy. So we saw that, and we found that there's a lot of intricate connectivity patterns. There are these feed-forward connections and point-to-point connections, convergent, divergent. There's these long loops which go over multiple modules in the multiple brain areas and come back to the origin. So there's all these things, right? So then all that led to an interesting question. Why are brain regions connected in such intricate ways? Is there any logic of brain's connectivity? Because if you want to understand what is special about brain's function, then we need to understand what is special about its connectivity pattern, right? And it seems to be there seems to be some kind of a conscious decision, a purpose, right, in packing various brain regions in that particular fashion, right, in the brain, because people have done some calculations and have concluded that if you take different parts of human cortex, right, and then instead of packing them inside the cranium in the order in which they're actually packed, but instead of doing that, if you just randomly shove them in the cranium, then brain will be sometimes 10 times larger, right, to maintain the same degree of connectedness. This is from Mitchison. So, like an analogy, we talked about how you pack a large baggage for when you go on, say, international travel. So to answer what is the logic of brain's connectivity, we need to first ask, why do you have a brain? What is the purpose of the brain? Right? Let us look at this. Let us visualize and try to kind of imagine what happens in this very simple scenario. So you're walking fast and suddenly you step on a pin, right? And then what happens? So you kind of take the foot back, right? And obviously you won't stop there, because if you just withdrew your foot in pain, and if you did not make any other correctional changes to the rest of the body, you will just lose balance and fall, because when you place that foot forward, your body must have moved forward. And when you just lift up the leg, without making sure you make appropriate postural adjustments, you will just fall forward. Okay, so obviously then when you lift the leg off, you kind of bend backwards a little and make sure you shift the weight to the other leg, which is still in contact with the ground. And maybe you will also kind of move your hands around so that you balance yourself with the help of hands. You might adjust your neck angle, your head position. So thing is, the stimulus that had triggered all these changes in the body is microscopic. It's just a dot. In response to that single dot, this huge body, maybe 70 kilos body, right, has shown huge global changes, and very rapidly. You won't even know that you're doing all that. All that happens automatically, right? So, and that kind of a coordinated responses at a global level, right, at the whole body level, is possible because of the nervous system. Right? That's obvious, right? Because it's the nerves that can carry impulses so rapidly. Now, it's not just humans, and not just even animals, but even plants have some kind of a nervous system. Only thing is, plants don't have like a distinct nervous system in anatomical terms, because anatomically, nervous system has all these fibers which have special electrical properties, and therefore they're able to communicate signals quite rapidly and all that. But in a plant also, for example, if you say in a tomato plant, right, if say when a kind of a worm starts eating one leaf somewhere, in the plant, right, immediately that will the leaf there will generate certain wound signals, right, and then that gets propagated, over the entire body of the plant. And then other parts of the plant now start releasing a chemical which can be harmful to the worm. So it will stop eating. So it's like, so when there is an attack on the plant in one small area, that signal is communicated, right? Some kind of alarm signal is communicated to the entire body of the plant, and the plant make correctional changes and takes certain defensive measures, right, to counter that attack. Now, there are obviously chemicals involved, but a lot of the signals are propagated or carried by electrical signals. Just like the action potentials and nerve signals in a nervous system, in an animal or a human, right? Plants also have electrical signals which propagate along the branches of the plant. Only thing is, these signals are much slower than what they are in human. So, for example, certain plants have action potentials. So, in an animal action potential, it's a very small event. It's a very fast pulse. So, it could be about 1 millisecond. Whereas in a plant, the action potential can be much longer. It can last for about 2 seconds. Other than that, there are electrical activity that coordinates the communications across the entire body of the plant. And a lot of this work, I don't know if you are aware, has been worked out quite beautifully by Jagdish Chandra Bose, Indian scientist Jagdish Chandra Bose, almost 100 years ago. He did his work in the early part of last century, and he worked out a lot of this electrophysiology of plants most extensively. He's written a series of books on that, but unfortunately, that work is not continued by none of the Indian scientists seem to be continuing that whole tradition. But this aspect of plants has been well worked out by J.C. Bose. Let me give another example, which is probably quite familiar to a lot of you guys, because most of you must be living in hostels, or at least there was a time when you lived in hostels, even though now you are far from hostels for a long time. Imagine a situation where you're all having some nice party on the hostel terrace, right? And some fun party, really fun party. So then all the lights are off. The lights are on, and suddenly the hostel warden comes for inspection. Okay, so if you are caught having the party on the terrace, then you'll be in trouble. Let us assume just a scenario. So what do? You'll obviously have some kind of guards, like guarding the entrance or something like that. So these chaps see the warden entering the hostel, and quickly the SMS all the party makers, right? And then the signals, the information spreads, the message spreads through the entire hostel. Right, all these fellows quickly rush to their rooms and shut their doors, and lights are off. And within maybe 10-20 seconds, the entire hostel is quiet and party has disappeared. Right. So basically, in this case also, there's a very small stimulus, a very local stimulus, which is say warden entering the hostel, and the response has gone over the entire body of the hostel, and the problem is solved, and there's defensive measures are taken in very quickly. So for something like this to happen, you need a network, right, which will carry information over the entire body quite rapidly. So all that you need is a system that can produce coordinated, rapid whole body responses, and that's exactly what a nervous system is meant for. So now there's one way to, so basically you need a system, right? Because the existence of a system is integral, is crucial for the survival of an animal, right? Because if you want to run away from a predator, you should be able to produce this rapid whole body responses, right? When there's an attack on the leg, you cannot leave that response only to that leg. The whole body should respond in response to that. So one way to achieve this kind of a system is to increase the velocity of conduction, because you want to get the signal around rapidly. One way to increase the velocity of conduction, because time is equal to distance by velocity, right? And higher velocity means reduced time. The other way is to reduce distance, right? Because again, it's common sense. If we reduce distance, time goes down. So there are two ways to achieve rapid signaling inside the body. Let us look at the pros and cons of these two mechanisms. Maybe we should use a combination, but we should have an idea of which is more feasible. So because if you look at the first strategy of increasing the conduction velocity, so how to increase conduction velocity? Because in a nerve fiber, it turns out that if you want a faster conduction of fiber, you need to increase the diameter. So in this table, so there are different kinds of fibers. So there are two things about it. One is the thickness of the fiber, and then the presence or absence of this myelin in this special sheath called the myelin sheath. Okay. Oh, sorry, this is not millimeter. This is micrometers, microns, right? And this other thing, this is meter per second, but the thickness is microns. So for the thick myelinated kind of axons, right, the connection velocity is about 35 to 75 meters per second. It can even go up to 100, 120 also in very good myelinated fiber. These are called type A fibers. In type B, which also has myelination, but the fibers are thinner, the myelin sheath is also somewhat thinner, and so these are 3 microns, right? And so you have an idea of how small the nerve fibers are, right? And speed is also much lesser, and the thin unmyelinated fibers, type C fibers, are even smaller, less than a micron, right? And their velocity is also much smaller. Now, if you want to increase conduction velocity, and if you want to take this route, that is, okay, I'll increase the fiber diameter and somehow I'll create a fast network. The problem with that is, if you increase the thickness of the fiber, and there's not just one fiber, there are like billions of fibers, right? Then the whole brain volume gets big, because we know that especially in larger brains, right, the fractional volume of fiber is higher than the fractional volume of the cell bodies. So large and thicker fiber means the volume goes up, so the brain volume goes up, and then so therefore to connect the same brain regions, right? Assuming the network connectivity is the same, so connect the same brain regions. Since the brain is bigger, the regions move apart, right? And then therefore you need to have even longer wire, and so distances go up. So achieve the same time delays, this small time delays, you need to increase the connection velocity even further, which means even thicker fiber and even larger brains. So you'll get into a kind of a vicious cycle, right? So this thick fiber is good, but if you overdo it, you'll end up with very large brains, and beyond a point, it will become self-defeating, right? So this is a problem with the thicker fiber route. What is the other strategy? Right, decrease the distances. So how do you do that? That is you decrease the wire lengths. How do you do that? So let us say I have a neuron here, like some kind of a test neuron. This is just a hypothetical situation, because we want to talk in terms of principles and not just look at brain details. We'll come to details later. I have a test neuron and I have 3 other neurons, 1, 2, 3, right? And this neuron is supposed to have send connections to all these 3 fellows. Okay, so then the question is, if I want to, so thing is, I want to on the whole minimize the transmission delays, right? Because it has to send signals to these 3 target neurons on various occasions. Now I want to make sure that the delays are minimum. So, and I don't want to spend more energy and material on having thicker fibers, right? So the given thickness of fibers, how do I minimize the delays, right? The simple answer is minimize the total distance, minimize the lengths on the whole, right? So if my neuron here is P and ABCs are target neurons which are fixed, okay, so if you want to judiciously place P with respect to fixed targets of ABC, then I just have to minimize the distance AP plus BP plus CP. Okay, and it turns out that this is a very nice problem from geometry, right? And this, so given a triangle, the point where AP plus BP plus CP is minimum, this is called the Fermat point. Okay, so it's an interesting problem, a mathematical problem. Now, so if you want to minimize delays, all other things being equal, if you you say there's a limit on the thickness that I want to go to because it gets too expensive beyond a point, then we have this other route, which is rearranging the neural masses in such a way that the wire length is minimized. Because that way also we achieve the same objective, but without spending any extra money or extra resources, right, on that design. Now, minimizing wire length is a very common and very important problem in circuit design, for example. The brain is a big circuit, right? Because neurons are like electrical devices, electrically active units. So in artificial engineering circuit design, This is a big problem while minimization. So, for example, there are many variations of this problem. So many situations where you end up, you ask the question of how to distribute certain circuit elements on a printed circuit board in such a way that the certain wire length is minimized. So take this toy example, what you say in the topmost picture, right? So there is a Boolean circuit, a bunch of logic gates, and there are 8 gates, right? Starting from 1 here to 8 here. They're all connected in some fashion. Now imagine I have to distribute these 8 gates onto 2 chips. Okay, please mute yourself. I have to distribute these 8 gates over these 2 chips equally, right? In such a way that the total wire that goes from one chip to another or across between the 2 chips is minimum. I'm not even asking to minimize the total wire length, because wire length is a more complicated thing, because right, the way we route these wires and all that, that's a more complicated calculation. I'm just asking, okay, just minimize the number of wires that cross over from one chip to another. So if let us consider 2 kinds of partitions. The first partition is this dotted line here. So where 1, 2, 3, 4 are in one partition, 5, 6, 7, 8 are another partition. If you do that, you can see that the number of wires which go out of 1, 2, 3, 4 to connect with 5, 6, 7, 8, there are 4 of them. So one, right, and you see that in this figure B. 1, 2, 3, 4 gates are in one chip, 5, 6, 7, 8 are in the second chip. So you see 1, 2, 3, and 4. 4 fibers go from chip A to chip B. No, 4 wires, sorry, go from chip A to chip B. Whereas take a more interesting, kind of counterintuitive, non-intuitive kind of a partition, right? Because anyway, the connectivity has to be preserved. Because this is a circuit, you need to preserve the connectivity pattern. But you are free to place them wherever you want. And only the constraint is that minimize the wire length or minimize the number of wires running from one chip to another. Because so basically, in this case, what happens is when the wire goes out, it will be a thick copper wire, which goes out of one chip to another chip. Inside the chip, all the wires are much smaller, much thinner. So they are cheaper. Okay, but once the wire goes out, it is a thicker wire. So you want to save on the metal. So if you do that, so you see that number of wires which, so 1, 2, 5, and 7 are in one partition, and 3, 6, 4, and 8 these 4 are the second partition. If you divide like that, there are only 4 gates in one chip, but the number of wires which cross over from one to another is this one, okay, and this one. So that's only 2. So you can see that here. Right, so this is a non-trivial problem, but so you don't have to spend anything to achieve this. It's just optimization. How do you group these things around in an optimal way so that you save some wire? Now, brain being a huge network, right, and so minimizing the delays, the transmission delays, is obviously a very important part of brain's function or any nervous system's function. So, like I said, instead of just depending on thicker fibers, which is not a very efficient way of going about solving the problem. So, just optimally placing the elements inside the fixed volume of the skull is a better way. And so that makes a lot of engineering sense. And in actuality also, you see this kind of a tendency to minimize total wire length in the brain. Okay, that's a more feasible route, right? You can get more mileage out of that principle rather than just increasing the wire thickness. So there's a nice paper by Cherniak, 1994, but there's lots of other papers on the same lines later, but this was one of the first papers that talked about component placement optimization in the brain. Now, component placement optimization is an expression that comes from electrical engineering, from chip design. This guy says same thing is happening in the brain. So that's the reason why I keep saying that if you take an engineering approach to brain, a lot of things just fall in place. They look like common sense. But if you just focus on the details and keep mucking up details, it looks very complicated. So let's look at the first example that Cherniak talks about. This is from an organism called C. elegans. We already talked about it. This is an organism which people have studied to work out the entire connectome, because this has only a small nervous system having 302 neurons. And The length of this organism is only 1 millimeter, diameter is 80 microns. So you can't really see it with a naked eye. You need a microscope, and you can see this fellow wiggling in the micrograph in this picture. Now, so if you look at a section of this and look at the locations of various ganglia. Now, ganglia is a term which we were introduced, I think, last class somewhere. So, like I said, in the brain you have masses of neurons which are connected by fibers, and these masses go by different names, and fiber bundles also go by different names. One of the names for the masses is ganglia. Okay, so the neural masses in the body of the nematode or C. elegans, they are called ganglia, and they form a network. And it is completely understood which ganglia is ith ganglia connected to the jth ganglia, that is known. And also number of fibers that connect ith ganglia to jth ganglia, that's also well known. So there are 11 ganglia, and some are closer to the head, some are close to the tail. And so this picture shows you all that. And this table, this matrix tells you the whole connectivity. So you can see the names of the ganglia, whatever pharynx and anterior ganglion, dorsal ganglion, so etc. etc. And the entries tell you. So wherever there's a non-zero entry, that means those two, the ith and jth ganglia, are connected. And the number shows the number of fibers. So if you take this problem, now what is the optimal connectivity among these ganglia? So what does that mean? So imagine that the worm is roughly one-dimensional, right? Although it's strictly three-dimensional, the other thickness and height or width are trivial and very small. So you can imagine all the ganglia as laid out on a linear scale. Imagine that the locations of the ganglia are fixed. So it's like a bunch of slots, right, along the 1D axis, and the ganglia are fixed in these slots. Now imagine that you are free to place any ganglia in any of these 11 slots. So there are 11 slots on the x-axis, and there are 11 ganglia. You can place any ganglia in any of the slots. Of course, a given ganglion can only occupy one slot. Now, depending upon how we have placed, this is a permutation problem, right? Depending upon how we have placed the ganglia. Okay, the connectivity pattern of the ganglia is fixed, right? You are taking the same network and rearranging the nodes of the network among these 11 slots. Okay, and since it's a permutation problem, the number of different permutations that are possible is 11 factorial, which is about 39 or close to 40 million permutations. Now, for every one of those permutations, if you calculate the total, you can calculate the total wire length because you know which ganglion is connected to which other ganglion and what is the number of fibers between every pair of ganglia. So you can calculate the total wire length, and it's quite surprising that the actual configuration of the ganglia in the real C. elegans turns out to minimize the total wire length. So if you take any other ordering, any other permutation, the wire length goes up. So that means C. elegans during its evolution has somehow figured out that if I want a network with this pattern of connectivity, this is where I need to place the ganglia inside my body, right? Then the wire length is minimized. And that's beautiful because it makes sense to minimize wire length from biological point of view. From engineering point of view, it's a meaningful thing, and you see C. elegans doing that. Okay, then you might say C. elegans is not a big deal. I mean, it's just one tiny little insignificant organism. Then let us look at more examples. So the next example comes from the cortex. It's a cat's cortex. No, actually multiple brains. So again, it is from cortex, and cortex in humans is a sheet of about 1600 to 2500 square millimeters, right? And it has about 50 regions. So these are called cytoarchitectonic, just a slightly pompous name. Cyto stands for cell, and architectonic, the tectonic comes from the plate tectonics, right now, which refers to these continental plates on the Earth's surface and how they move against each other, all that stuff. Here, cytoarchitectonics is basically the kind of regions on the brain surface. So people have classified the whole brain surface into small regions, depending upon the types of cells found in a given brain region. So combination of cell types found, right? Just like you classify soil types, right, on the Earth based on the type of soil present in different parts of the region, parts of the earth. Right? Here also based on the different cell types present, people have classified different brain regions. These are called Broadman areas, named after the person who did some of this early classification. And so there are 50 such areas, so you can name them. And now, so also you cannot see connections, right? So this picture shows all these areas. You cannot see these connections much, but there are fibers, and a lot of the fibers. So in the brain, if you look at the cortex, so let's take a small patch of the cortex. There are, each neuron is connected, has lots of local connections. So it is connected to neighbors, like that. It also has long range connections, but slightly longer, really longer ones actually go into the mass of the brain and then go back up and make connections with other neurons. So short range simply are nearby, so they are all confined to that same. So cortex has these layers, right? I talked about 6 layers of the cortex. So in this lab, short range are all nearby, happening, going through the same, through the cortical layers themselves. But if you want to go make longer range connections, right? Usually the neurons dig deeper and then make connection to the other side. Also, that sometimes makes sense because usually the cortex surface is not like a plane. It's not flat. The cortex surface has lots of undulations. So if you have a cortex like that, right, and if you want to make connection from here to here, it makes sense to dig through like that. Okay, instead of going through like that. Okay, that's another reason why these fibers which make connections go through the volume of the brain. Okay, sometimes when you go from one side of the brain to the other side, so let's say this is hemisphere, and so you're here, and then this is left brain, right brain. You want to make connection between left brain, right brain, and there's actually a bundle of fibers called corpus callosum, which make these kinds of connections between left and right brains. So fibers from here will go deep into this, so there's a core, right, where two hemispheres are joined, goes through this and go back there. Okay, so these connections obviously cannot see in this picture, but they exist. They go through the volume of the brain. Now, so these connections are all worked out, right? At least at a gross scale, maybe not at single fiber level, but at gross scale, these connections are worked out. Now, let us look at cat's visual cortex. Okay, they have taken 18 cortical areas. Now, so they have taken a bunch of regions, and then they're asking the question, if two regions are contiguous, that is, are they next to each other? So here, for example, region 8 and region 6 are next to each other. Okay, similarly, region 19 and region 18 are next to each other. And this is also next to region 17. So this is called contiguous. Okay, then connected is something that you cannot see in this picture, but for example, 17 and 18 are connected, right? And probably 18 and 37 are also connected. I'm just guessing, but you need to really look at the table. So they look at the number of pairs which are connected and the number of pairs which are contiguous. And they find that very often contiguous pairs are also connected. Okay, statistically, there is a high probability that if two regions are contiguous, right, then they're also connected. So what does that mean? It means that there's a tendency to minimize wire length, right? So because if two regions should have minimal wire length, you're better off. So two regions are connected, right? And therefore, to minimize wire length, you will try to bring those two regions as far as possible close to each other. Okay, so contiguous cortical areas are more likely to be connected. So they have taken data from cat's visual cortex, rat olfactory cortex areas, and C. elegans ganglia. In all these cases, this correlation between contiguity and connectivity is much higher than chance. This is what this statistics tells you. Next, let us look at this very interesting problem of brain position. Right now, why is the brain in the head? So suppose you are God, right, and you want to figure out, okay, you made the body and you made nervous system. Now you have made the brain, not because you want something which will fill the entire body, so that you can have this fast signaling network, right? So that the whole body can respond as an integral whole and rapidly respond to outside stimuli. So you have created that kind of a, you're a super genius to create this kind of that kind of network. Now you have a very interesting decision to make. Where do you put the brain? What are the criteria, like some kind of design criteria for this placement? Any questions, any answers for any ideas? Because brain in us, right, is in the inside the head. But is that the best place to put? Why not inside the chest? I mean, look at this. Right? What you actually have is this, and is that the best thing to do? What are some design criteria for brain placement? Anybody? You can unmute yourself quickly and give an answer. Blood-brain barrier, how is that? What does it mean? Aditya, go ahead, explain. Abhiram, well protected, very good. Okay, so you are saying that brain is well protected if you put it in the head, right? Because cranium is hard and it gives good protection. Yeah, it's true, but it's only partly true. Actually, putting brain in the head, it makes it very vulnerable. It's not really protection. So why is brain vulnerable if you place it in the head? Because apparently it's inside the skull, so it actually seems to be quite safe, right? You kind of bang your head on the wall a little bit, you're still okay, right? So I'm saying brain is actually quite vulnerable if it sits in the head. Where is the vulnerability coming from? Any other suggestions? You can type there. I can see in my little text box here. What is vulnerable about a brain sitting in the head? Okay, the answer is neck. Neck is the weakest link. Right? I don't know if you see in the olden days when high gravitational head. What is that? It takes a lot of energy to against gravity. Yeah. So it takes a lot of energy to pump blood into the brain, but looks like that's still okay, right? That energy cost seems to be okay, but so that means if you take all the trade-offs, somehow body finds it still okay to put the brain in this highest point and then pump blood to it, right? And even not bother about the vulnerability of placing the brain in the head, and then the neck is vulnerable. And also, if you see, neck is the weak link, yes, because I don't know if you've seen in the olden days in these wars where people used to fight with large swords, right? They go for the neck, right? And because the neck is the part which is easiest to sever and put an end to the life. So I mean, sorry, it sounds violent, but chopping the head off is like a big deal, like a mark, it's a sign of a warrior and all that. So anyway, let's leave out the gory stuff for the moment. Neck becomes a vulnerability if you place the brain inside the head. In spite of that, evolution has chosen that position. So but there must be some other advantage in placing the brain inside the head. Let us see what that advantage is. So what is special about the head? Right. Now, to answer that question, let us go back, because the thing is, if you ask this question in human context, it is difficult to answer. You should look at the evolutionary history. How did it get there? How did the brain get into the head? Why is in the head in the first place? So to answer that, we need to look at this more basic, go back into history a little bit. A typical organism has a kind of a longitudinal axis, right? A typical organism, a lot of them, not all, but a lot of organisms are simply like a little tube, right? Like a cylinder, which is quite long. So then typically they are horizontal. I mean, if you start with even your favorite C. elegans, it just looks like this, like a little ellipsoid, like a prolate ellipsoid which is stretched, elongated, right? And in this ellipsoid, there is, so it looks like this is a long axis. Now the question is, there are certain neurons inside this somewhere all over the body, and these neurons connected to something in the body outside, so that they make connection with the outside world. Because they are connected among themselves, they are also connected to the outside world. How are they connected to the outside world? By two things. One is sensory organs or motor organs. Only two things through which a body interfaces with the world. Sensory organs take measurements from the world and give the information to the body. Motor organs act on the world. You can act through legs or whatever, antlers and whatever it is, something active. Okay. Sensory organs could be like eyes and things like that. So now the question is, where do you place the head? Right? Or let me ask a question. If I have a bunch of sensory organs like this, right? Where do you place the sensory organs? Where to place? Imagine I have the option of placing sensory organs all over the body, uniformly distribute them all over the body. Will I do that, or will I pack them all in one place, or where do you do that? What's the best place to place them? Or let us ask even more fundamental question. If I think of a body, if I'm a mathematician, if I think of a body, right? When you think of an object, what do you think of? Like a dot or just a ball? Because for a mathematician, it's most convenient. Think of a body as a ball. Why aren't bodies like balls? Why are they like tubes? What's the advantage of this ellipsoidal or tube-like structure for a body? Can you ask such fundamental question and think about a little bit? Any comments, remarks? Yes. Hello. Okay, let me give a small analogy. So let us say a bunch of you, go to some mall like on a weekend, right? And mall is busy, lots of people bustling with, right, customers and all that. And let us say some 6 or 7 of you go to the mall. Easy to grip. Wait a second. Okay, 6 or 7 you go to the mall and you're walking in the corridor, right? You're all close buddies. Now, what exactly will be the formation that you will form, right, when you walk through the corridors of the mall? You understand my question? It's a busy mall. Some 6 or 7 of you are going together, very close friends.
In a line,
Right?
sir.
Sorry? How?
In a line.
In a line? Is that actually you guys how you go in a mall when you go to a mall? Like children forming a train. Is that how you go? Circular. What do you mean? Random blob is problematic. Okay. What are the two extreme configurations? Actually, what do you see? A bunch of youngsters, walking together in a mall. What is stick together? Yes, but what exactly is the shape of the configuration? Hexagonal close packing. No, tell me, what do you guys do? Forget about the math. What actually happens in reality? Triangular? Is that how you go? Like 6 people, 7 people, they form a triangle? Smaller groups? No. Very often what you see is they forming like a horizontal, a parallel row. Because nobody wants to stand behind. Yeah, something like that. One. They're all forming a parallel this thing, right? Nobody wants to stand behind because you lose the fun, you miss the fun. You can't see what's in front of you. So they all stand in parallel. Okay, and everybody they kind of shoulder to shoulder they stand and walk forward. Is there a problem with that configuration? Yeah, if the mall is crowded, that's not optimal because somebody will yell at them and say, "Hey, you're blocking the entire corridor." Right? Break up. Right? That kind of configuration is not sustainable. Right? It is fun for you guys, but it's not sustainable. Somebody is going to yell at you, and then that formation gets broken up. And then let us say you keep on getting pushed by people around you. What is the most conservative, simplest, stable configuration that you will occupy? You started off with 1111, all standing in parallel, right? People are putting pressure on you to break up that configuration. What is the safest configuration where you will happily let go? 7 people, not just one. One behind the other, very good, right? That's the correct way. That's safest because nobody will bug you, right? So you will be one behind, go one behind the other. It'll be like a bunch of kids playing the choo-choo train in a kindergarten school, right? And the advantage of that is it's flexible. It's like a snake. And no wonder some of the earliest organisms in a working, which have lived in a fluid medium are reptiles. Because that's a very convenient evolutionary, very convenient and stable, configuration, right? These are called body plans. What are the shapes of the body that evolution comes up with? And that depends also on the medium in which that organism, that the species grows. So a snake-like body plan is a very convenient thing, right? Therefore, this kind of a longitudinal animal bodies which have simply like a tube-like shape, right, is a very logical thing. It makes sense. It gives a lot of evolution advantage because it is less it's not very confrontational with respect to the surrounding environment. So you end up with this kind of a tube-like body plans. Now let's come to the question of sensory organs, right? You want to measure the world because if you let us say you form this train-like configuration, you're going in the mall, and let us say the first guy has very poor eyesight. First guy in your train has very poor eyesight, and he forgot his glasses. Now, if you walk like that, what will happen? Right, you'll keep bumping into people, and then you will get into more trouble. So, what do you want to have? The people who have good eyesight and good vision or good hearing and all that. These are the kinds of guys who should come and stand in the front. Right, people who don't have good sensory systems should go back somewhere, right? So, just taking that analogy forward a little bit, if you are going, and if the body is like a tube, then the advantage is it can dig through a surrounding medium, which resists it, right? It can dig through more efficiently because it's like a thin tube and it has a sharp kind of pointed tip, right? And now when you are measuring what is there, around you, concentration of chemicals or temperature gradients or whatever visual information, whatever it is, pressures, the pH, whatever it is you are measuring, you want all that measurement to be done by the vanguard, the frontmost point in the body. Because the frontmost point in the body is the one which comes into the world, comes into contact with the world first, right? So the measurements of the world must be taken at that point by that part of the body, because then it immediately communicate those measurements to the rest of the body and says, oh, hey guys, there is something hot I've just come into contact with. So I'm going to back up, or I'm going to turn around, or turn away from this. Or there is some toxic chemical here, right? I need to turn around, right? Or there is some kind of food source, so I'm getting very good, right, olfactory signals, so I need to go forward. Or I'm hearing some, getting some pheromones, so somebody is attractive here, so I'm going to go forward. So your measurements must be done by the front of the body, the frontmost part of the body. So you're better off packing all, or at least a majority of your sensory apparatuses, right, in the frontmost part of the body. So then if you do that, right, then okay, so we have argued up to that point. Now the next comes the question, where do you place the brain? Okay, let us ask that question. So let us again ask a very hypothetical thing. Let us say I have this is the body, this is my body, and I have 2 eyes, right? There's one eye here, and some nose here. And I have some kind of a brain as a bunch of neurons, right? These neurons take inputs from all these eyes and the nose and all that, and communicate those results to something in the back, maybe to legs or whatever, cilia or whatever is there, the other parts of the body. Now the question is, right, where will I place this brain? Okay, so let us look at some hypothetical situations again. This is the body, and let's say these are 2 eyes, and I have only just one neuron, okay, like a really small pathetic nervous system, okay, which has just one neuron, and that is connected to one leg here, and to another leg here, right? Something like that. So now, so I have two fibers going to the eyes and two fibers going to the legs. Where will I place this one neuron? So this stupid nervous system has only one neuron. Where will I place it? Because I want to minimize the wire length, right? So I'll place it somewhere in the center, exactly in the center, so that the total wire length is minimized, right? Now consider what will happen if I have more fibers going into the sensory side compared to the motor side. Okay, so if I do that, then where will the brain go? Where will this neuron go? Because there's more fibers coming from the sensory side. If you want to minimize the total wire length, I'm forced to move the neuron closer to the eyes, right, and farther away from the motor systems. And imagine if this tendency goes further and further. You have lots of fibers coming from your sensory organs. So sensory organs are in the front, right, because for all the reasons I explained, right, and then for some reason assume that there's a lot of fibers coming from sensory organs to the nervous system, which is deep inside the body. Then the nervous system will automatically tend to come closer and closer to the sensory organs. So which is what happens in evolution. And because of this, you will typically see as the organism grows larger and larger in evolution, starting from a simple organism like C. elegans, as you go to larger organisms. So you will see that the brain part will come closer and closer to the sensory organs, right? And in fact, that becomes the earliest version of what you later on call a brain, right? Because of all the sequence of developments, the bodies will start developing some kind of a mass of neurons, which is close to the sensory organs and which are close to one end of the body for all the reasons I explained. And so that's how kind of brain-like structure develops. Now let us look at this data, right, and what it is like in humans and and again in C. elegans. So the number of fibers connecting the brain to the sensory organs, right, and the brain to the motor or something in the back of the body. So these are called anterior connections, right? Anterior connections, and these are called the posterior connections. So look at these now. Let's look at these numbers. So in human case, so human is not like a tube, but it's not a horizontal tube. It's a vertical tube because humans stand erect, right, on two legs. Now the anterior connections are all the connections from the brain to the sensory organs, to the eyes and nose and everything. So olfactory is to the nose, optic is to the eyes, oculomotor is also to the eyes, and so on and so forth. So all these cranial nerves, which we'll discuss later, which connect from the brain to the various sensory organs and some parts of the head, right? All of them, the number of fibers, total number of fibers in all these nerves comes close to 13 million fibers. So head is a small volume, but if you actually count the number of fibers going from the brain to the sense organs, it's a very large number compared to all the fibers that go from the nerve system to the other parts of the body. Okay, so in the other parts of the body, you not only have motor organs, but you also have this skin, which is a huge area, right? But which is fed by all these spinal nerves. But even if you take all that, it looks large in terms of area, right? But the number of fibers that connect the rest of the body to the spinal cord, right, is actually much smaller than the number of fibers which connect the brain proper to the sense organs in the head. So the first set of fibers, that's about 13 million, right? And second set of fibers is only 2.5 million, 2.4 million. So the anterior posterior ratio is nothing but this number by this number, and that happens to be some 5.25. Okay. What is the corresponding figure in a much more primitive organism like the C. elegans? The anterior connections is only 146. The posterior connections is 96. The ratio is close to 1.5. 1.5 here versus 5.2. Okay, so this tendency to have more and more anterior connections, right, compared to posterior connections is seen as you go higher up in evolutionary ladder. Okay, and all these things. So for this reason, you also see tendency to development of some kind of a brain-like structure, right, in higher animals. So I think let us stop here, right, and let us continue In the next class, we'll look at different kinds of species and what kind of nervous system they have and what is the logic of that. And I'll show you some very simple simulations that we have done just to show how this logic can explain the formation of different kinds of nervous systems that you see at different stages of evolution. Okay,